Hello again and welcome to another video. Today we're gonna explore using MATLAB to simulate a simple pendulum system. And since I chose the simple pendulum system because today is just an introductory video about MATLAB, and I thought that the simple pendulum is one of the easiest and one of the simplest physical systems, and so it would be a good way to introduce generating simulations using MATLAB. And so, first of all, we would have to declare some variables. We would have to find a way to define some variables that we're going to use in the code before we actually move on to the coding part. And so, let's draw first what a simple pendulum system looks like. You have a mass that is hanging by a string that has a length of L and has a mass of M. There's only one variable. There's only one, it's a value that changes, and that's going to be theta. And theta is an angular quantity. And so in order to define theta, we would have to define, of course, theta, the starting theta. We'd have to define the angular velocity and how the angular velocity changes. I say just theta because theta also changes by time. So we would have to define these three variables, and one which is not necessary but I would also want to do is define the tension and see how the tension changes according to what happens. Alright, so in order to do this, I'm going to imagine zooming into the mass, and we're going to draw a free body diagram. Let's say this point mass is the center of mass of the mass, that is of the bob that is swinging, and we have the tangential path that this would take. So imagine zooming in, and the curve, the circular path, would going to be a straight path if we zoom in very close. And then we have the normal direction. And you're going to see why I divided the trajectory or the motion of the bob into two perpendicular components. I'm going to define this direction as the tangential direction and this direction here as the normal direction. And we have, of course, the weight of the ball directed downwards. Whichever direction you look at first, it doesn't matter, but I'm going to look at the normal direction first. So what do we know from Newton's second law? We know that the net force in any direction, in this case I'm going to say the normal direction, is going to be equal to the mass times the acceleration in the normal direction. And we know that this value now is also equal to, imagine what forces there are acting in this direction. First of all, we have this force over here, which is caused by the weight, which is equivalent to, because this here is angle theta, we could say that this angle over here is also angle theta. And so we could say that this here, so we could say that this here is equal to mg of cosine of theta because it's the adjacent side, the magnitude of this force. And we also know that there is another force. And maybe the magnitude is quite misleading, so I'm going to shrink the effect of gravity because we know that tension must be greater. Yeah, so that's mg cosine theta, and let's say there's another force here that is caused by the string pulling onto the mass, and we're going to call that Ft, which is tension. And so we know that the net force, therefore, is equal to Ft, which is the larger force, minus the retarding force, or the force that is in the opposite direction of tension, which is mg cosine theta, caused by the weight. And so we have an expression that goes like m an is equal to Ft minus mg cosine theta. And so Ft, what we're going to define here is Ft, not T, f of t. We want to define f of t. And we have an expression of f of t that goes like this. But still, acceleration in the normal direction, we haven't defined that thoroughly yet. It's by doing this, we're just adding one more variable. It doesn't really do anything. And so we would have to define the acceleration in the normal direction. We can do this by what we learned about centripetal forces. After all, this path caused by this path taken by the mass is basically a circular path, because the radius is constant, in which the radius is constant. And therefore we know that, well, we learn that acceleration in the centripetal direction is gonna have to equal to v squared over r. And in this case, r, the radius, is equal to L. And what do we know about v? Well, here, I kept mentioned the angular quantities. And we are dealing with angular quantities because theta here is the variable we have to define. And so we have to define everything in terms of the angular quantities, not the linear quantities. But luckily, there is a very convenient way to link the linear quantities and the angular quantities. And it is that to get the linear quantity, we just have to multiply the radius to the corresponding angular quantity. Well, we could prove this by looking at a circle and saying that, well, if arc length is the linear quantity and theta is the angular quantity, well, we know that arc length then is going to equal to circumference, we're saying that's r, times theta over 2 pi, because that's a ratio that theta takes in terms of the whole pi, and so we get is equal to r theta. And L is basically the displacement, S, the total displacement. And so we get, because we have r equals r, S equals r theta, we could differentiate both sides by time, and basically we get, well, ds over dt is velocity, is equal to r times d theta over dt is omega, which is also equal to r theta dot, which is basically means the time derivative of theta. And we could do the same thing once more, and we're going to get acceleration, do the same thing, dv over dt is equal to r theta dot, or we could say r alpha. And so in every case, we have the angular quantity, we multiply it by the radius, we get the linear quantity. We have the angular quantity, we multiply it by the radius, we get the linear quantity. We have the angular quantity, we multiply it by the radius, we get the linear quantity. We get the angular quantity multiplied by the radius, we get the linear quantity. And so here we have v equals v, which is the linear quantity, is equal to r times theta dot, which is the angular quantity, or omega. But here we're going to stick with theta because that's kind of the variable we're dealing with. It's basically the same thing, but representing everything in terms of the same variable, it looks more cleaner, let's say. And so we have v equals. We have used this here, so, right? Yeah. So we have v here is equal to r times theta prime, or theta dot. And so then we could, well, r is equal to L in our example here. L is our radius, so we get L squared theta dot squared over L, and that's going to be equal to L theta dot squared. And so a acceleration in the centripetal direction, and that centripetal direction is our normal direction. So you could just replace this by our normal direction here. And so we get, when we substitute this value into our acceleration in the normal direction, we get ft is equal to L theta dot squared plus mass times L theta dot squared plus mg cosine of theta. That's our tension. So let's write that down here. So that's the first part done. We have derived the definition of the tension by looking at the normal direction here. Let's see if this matches if this is logical. Let's say theta is equal to, let's say, 0 when the mass here would have the greatest velocity and the minimum height. Well, then we know that there is no acceleration, there is no acceleration in either right or left in the horizontal plane, and because it is in constant velocity, we know that, well, the net force is 0, and so the vertical force and the downwards force will be equal. And so tension, which is the only vertical force, and gravity or weight, which is the only downward force, must have the same magnitude. And so let's plug 0 into this equation over here. Ft is equal to m L theta dot squared, which is equal to ma, as we said before, a. And this term is cancelled because cosine is eliminated, because cosine 0 is equal to 0. Cosine 0 is equal to mg cosine cosine 0 is equal to 1, so only mg survives. And look at this term, theta prime, which is the angular velocity. We define here that theta is increasing, and then at this point onwards theta will start decreasing, which means that the velocity, the change in theta, would be 0, exactly 0 at this point. So this term is cancelled and we only get mg. And so this proves that this model does correspond with our pendulum in real life. And so that here is done. I got the definition of our tension. And now moving on to the tangential direction. Now when you look at the tangential direction, it's even simpler. We only have one force acting on the tangential direction, and that is, well, the effect of gravity that is in the tangential direction. That is the only force acting on the tangential direction, and we know that that here is our opposite side, and so it's equal to mg sine of theta. And so net force, again, referring to Newton's second law, we have the force in the tangential direction is equal to mass times acceleration in the tangential direction is equal to mg sine theta. Alright, that's easy. Then we get acceleration in tangential direction is equal to mg sine of theta. No, g sine of theta. Now, acceleration in the tangential direction. That is basically when we have a circle. I regret I shouldn't have erased this over here, but when we look at the circle again, we had the tangential direction basically refers to the linear and angular relationship once more. And we have established that whatever the angular quantity is, to get the linear quantity, we multiply it by the radius. And so if we do the same thing here, we get, well, let's multiply the radius. This here is going to be equal to the radius, which is L, times our angular acceleration, because this is linear acceleration. And so we get theta prime prime, theta dot dot is equal to g sine of theta. And so theta dot dot is equal to g sine of theta over L. Now, I could end here and get a perfect model for a pendulum. But if you want to get more realistic, we want to have some retarding variable. We want to have some variable to get the pendulum to slowly slow down. And so that after a lot of time, it would be close to just wiggling really slightly here. It won't never stop because, yeah, it will never stop, but we want the pendulum to be as realistic as possible, whereby there is a retarding variable. And so we're going to subtract a variable that varies with the angular velocity, which is going to be c times theta dot. And so this basically means that the angular acceleration decreases as the faster the angular velocity is. And so, and so we have our second variable. We have defined our second variable, which is equal to g sine of theta over L minus c theta dot. Now you might ask, well, there are two variables more that we have to define, but that is not a problem, because what I'm going to do when I go on to the coding part is that I'm not going to see time as a continuous variable. I'm going to define time as a linear vector, as a column vector, which is comprised of 0 seconds, and then 0.01 seconds, 0.02 seconds, 0.03 seconds, and so on. I'm going to see time as a discrete variable. And what I'm going to get, for example, let's say we have a graph for theta. Theta is going to be keep oscillating, right? But what I'm going to get is not a continuous graph, but a graph that looks something like this. So let's say I drop the bob here when theta is pi over 2, 90 degrees. And then the graph would look something like this. It's going to start here, and it's not going to be a perfect cosine graph, but it's going to be composed of small dots that record each value of theta as time passes with dots since I'm going to define time as a discrete variable. And I have to do this because this is the only way to show to depict the change in time onto a simulation in MATLAB. In my knowledge, there is no way of defining time as a continuous variable and showing an animation that shows this graph and this movement. I don't know why, but that's how it is. But this has its advantage, because then we don't need to define all of these variables, like from theta dot. As long as we know theta prime prime, which is the angular acceleration, we could define, well, first of all, we could define theta as theta. Let's say we have a function theta of time. So time, we're going to input and all of these discrete variables and get a result. And for example, let's say we're going to have to calculate theta of 0.01. And then what we could do is say, well, then that's going to be equal to theta of 0 plus theta dot of 0. Because we're basically adding. So when we say theta at 0.01 seconds, that's theta at 0 seconds plus the change in theta times the time. And then we could do the same thing for theta dot. If you want to know what theta dot would be at 0.01 seconds, we get theta dot at 0 plus theta dot dot at 0. And theta dot dot at 0, we know it's this. And so here it would calculate theta dot dot, input it back here, and then it would do an infinite loop and get a continuous result, a discrete table of results that is going to be plotted onto something that would look like an animation and the graph. And so that's going to be the path I would take in simulating the simple pendulum. And so moving on to the coding part.